Hello, good afternoon, everyone. Today, Shivang, Rena, and I, Soumya Methani, I'm going to be taking you through the journey that we've had in the past couple of months, which has been all about converting or migrate, or rather migrating NoSQL to a distributed SQL database. We're going to go through all the ups and downs that we've faced, the best practices that we've seen, and the lessons that we've learned. So, going ahead, before we go ahead, basically, I'd like to tell you a little bit history about Helpshift because the examples are mainly concerning our own use cases. Helpshift, our company, is basically a mobile and web first customer service platform. And how we communicate, or how rather it's used, is there are two sides to it. There is an end user who can go to their own platform and complain about whatever problem they're facing to a customer. And then that is the screen on your left hand side. And then there is the screen that you see on the right hand side, which is basically the customer interacting with the end user and trying to solve their problems. So that's the platform. We provide this particular platform, this whole platform as a whole. So this, if you look at it, this whole thing where the end user and the customer is interacting with each other is what we call conversation in our company. And in this conversation related database, the entities that we encounter generally is, on the whole conversation itself is what we call an issue. And the actual text that these two major people, like the end user and the customer, are using is what we're going to be calling messages. Now, since they are the major entities, of course, if we create a data model for it, both of them have their own tables. Now, when we decided to start the journey of Helpshift, we chose MongoDB as our database. And as we know that MongoDB is a non-relational database, that is a NoSQL. So over the years, we added quite a few fields. We added, modified our structure, and the final structure that we have today, on the day that we are migrating, looks something like this, where you have an issues collection, and then you have a messages collection, and both of them have different attributes related to it. Now, these attributes are not in the most normalized way, but uh, they are in a very denormalized way, but that's primarily because of the database that we chose. We are going to be migrating this in the exercise today. We're going to be migrating this into a SQL model. So, what happened? Like, why did we decide to go with SQL? Is because our scale increased and we encountered quite a few problems with the current data models that we had. And then we started reevaluating our model and deciding what do we need going ahead, which was one was that we need to maintain all the conversation data with an end user at one place. We need data integrity, that is like any effect that a message has to an issue should happen in the same particular flow. So if one of them fails, the whole thing should fail as one commit itself, which is indirectly what transactions provide. And the last thing that we needed was scalability. That is, if tomorrow our scale increases to 100x, we can provide that to our customers without any failures going ahead. So with scalability, the problem was that we did not have a sharded infrastructure currently. We had just had a replica set structure, and ideally what we wanted to do is go into a sharded data model. Now, we contemplated the different databases that we had currently in production, and some of the ones that we thought fit our use case best. which is MongoDB, Scala, CockroachDB, and YugaByteDB. Of course, we were exploring sharded and transactional MongoDB, and same for all of the others. And what fit our use case best was YugaByteDB. I am not going to go too much into the details about what problems did we encounter with the other databases, because that would be a talk of its own. Now, like this sounds pretty exciting, right, to any developer. So we embarked on this journey of converting NoSQL to an SQL after having a background of 10 years in NoSQL. So that was like a major challenge for us, and we decided, hey, let's go on this major journey. And we saw around like couple of problems and couple of fun challenges that we encountered, and we're going to go through them one by one. The first thing that, of course, like the first thing that comes to your mind once you think about going from NoSQL to SQL is the relational part of it, making your data model relational, right? So normalization was the first thing that you had to do, because over the years, of course, your data structure becomes denormalized. And this data structure, what you're looking was what we had in production currently, which has a couple of fields related to the issue attribute, couple of fields that change depending on some other attribute, and so on. So here I have an example of one such document that we have in production. And as you can see, there are some JSON fields here. There are some fields that kind of depend on the running state of the issue. So basically, it's a jumble of everything into one. Now, the first step that we decided how to normalize would be to think about, take a step back and think about all the attributes that are only specific to an issue, that are very specific to an issue and that don't change depending on the type of issue that is there. Right. So we found all of these fields, which is ID, platform, fresh, and all of these other fields that we have there. And we created an issue table out of it. Now, the next step was segregating all the fields that we know for sure are there when there is some running state, right? So as you can see here, we have a bot state, we have some bot supported things. So all of these were fields that we knew are kind of related to bots and bot and issues running state. So we created a separate table called as issue chatbot state, and we kept some fields in it, whichever were necessary for us. Similarly, we've created a couple of other tables separately, which is primarily what normalizing does. And then we had this huge question about a field called as meta, as you can see there. Okay, what question did we have? Now, meta was basically a JSON in our MongoDB data model, which had a couple of fields, which is developer language, detected language, device language, respond to device info, and extra. Now, the first three were always present. The languages basically were present for all types of issues. But the next two fields, which is respond to and device info, depended on the type of issue that you had. So, for example, if it's an email issue, it would contain respond to, but it wouldn't contain anything else. Whereas if you have mobile issues, it would just contain device info. Right. So this is just like two examples that I've given, but there were like many such fields, around like 7 to 8 such fields that were there for something. And then there were just 4 different fields that were there for some other type. Then there were some 15 fields that were there for some third type of issue. So this was a major problem for us because these fields could be added as and when needed, depending on the feature that were being added into our platform. Now, we looked at all the solutions that we could find, and there are these 3 solutions that we kind of explored or dabbled into. The first one being, as normalization tells us, creating new tables for these, right? Creating a separate table for each of these. Like, for example, for email issues, you create a separate table. For Android, you create a separate table. Right. So we explored this and found that there are some advantages and disadvantages as it is. The advantages being that, of course, it would be a normalized structure. It would have structured data, if you can look at it, and you can control the number of field, the number of fields that are there in a table. The disadvantages being that there would be too many tables ultimately. There would have to be many things that would have null characters. There would have to be like the schema needed to be updated every time there is a new attribute or a new field to be added to the issue. And ultimately, it would also be quite time consuming for us from the code changes point of view. So this did not really look as a very attractive solution for our use case. So we decided that, hey, let's explore something else. And the next one that we found was entity attribute value model. Now, I don't know how many of you are aware about this, but entity attribute value model is something where it's you have an entity, and the type of like the entity itself, there are three basic fields that you have. So the first field is like entity, the other is attribute, and then there is the value that you store for this particular entity. This entity could be anything, and again the value could be anything. So you store separate values for different data structures many a times. So I'm not delving too much into this because we have a lot to cover right now. We can of course talk about this later separately. Now, the advantages that you have had to this kind of a model was that it would provide you a lot of flexibility, as in you could add any field that you wanted. You didn't have a restriction on the kind of field that had to be added. And on the fly, whenever your new feature is added, it's pretty easy for you to add any field. The space efficiency, because null fields don't need to be there anymore in the database itself, so you won't even have an entry for it. The disadvantages being that it would have multiple table joins, because you have a lot of tables now and you need to join all of it to get one particular thing, which was quite frequent for our use case, as in you needed all the data together in our use case. Additional logic would have to be written in the application layer for comparison, which would automatically be provided by the database in a conventional schema. The table size itself, since you don't have a bound on the field, you can just keep like adding any field that you want. The table size itself might go out of bound. So again, due to all of these disadvantages, we decided to go against entity attribute value model at present. So what did we choose is this third approach that we kind of thought would be best suited for us, which is that creating a single field, which would be of JSON data type, and it would store all of these extra fields that would be there. Now, the advantages here, again, you're getting flexibility because you can add any field that you want here. Of course, with flexibility comes the unlimited entries disadvantage that we talked about previously. The other advantage that we had is that this provides us, or this gives us an opportunity to put least efforts over there right now, because we already have a humongous task in front of us, that is migrating everything and migrating the data model itself and all of the other things that we had to do, and mitigating this problem for later. That is, as in like tomorrow, if we want, we can just remove this one field from the table and create a separate data model, as in use EAV or normalization as the technique. So this kind of mitigated our problem in present condition, so that we can choose a proper solution later and just keep the JSON fields. But again, there are two other disadvantages that you have here. One is the space of the object, as in the size of this field itself, because of unlimited field entries, just keeps on exploding sometimes. And the other being is that you cannot have any index on any of the fields or any of the extra data that is being stored in this particular field. All right. Or rather, not that you cannot have, it's just that it's kind of not very sturdy indexes on a JSON field. So given that we chose the JSON field, what now our original issue object looks like is there are three tables that it's divided into. The first, as we spoke about, issue table, issue chatbot state table, and then we had an issue meta table, which had some compulsory fields, as you can see. And then there was this extra field called as extra, which is kind of the meta, which is storing all of these fields that are being created on the fly depending on the issue type. So this is in general how we solved our problem of normalization. Now we did solve the problem of normalization, which is well and good for new objects that are being created in this particular way. But what happens to the old objects that are already present in our database? So we have to migrate those also along with the new objects, right? So we realized while doing it itself that migrations actually can get really tricky when you actually change the whole data model. One of the major disadvantages that we saw was that since you are in an SQL mindset, what happens is that I can just on the fly add a field today, right? So when I'm adding a field today, it's not necessary for me to add that field to all the documents, but it is necessary for me to do that in SQL, right? So let's say I add this field called as version today. So it will be present in all the documents from today, but it won't be present in the documents before today in MongoDB. Now, when I'm migrating this, I have to take care of the fact that I have to provide some value, default value, while I am converting it into an SQL data model. And it either has to be there. So it's not necessary that this default value has to be there in the default of your table creation itself. But while inserting the object, this value needs to be there, right? Unless and until it might be null, which again, you'll have to pass null and put null over there. The next problem that we encountered here while migrating was that the data type could have mismatches. What I mean is that, some data type might be allowed in an old database, in a NoSQL database, but in a SQL database, it might not be allowed. For example, one of the things that we encountered was null characters were not supported in Postgres. And many of the fields in our messages, like the body in our message, might contain null character which are being added by the agent or some user, right? The next thing that we encountered was that the chunk size, while you're migrating, the chunk size kind of depends on some variable limit. So this is called as the bind variable limit, which is a combination of the number of columns that you have into the chunk size that you are actually inserting. So you, like, even though it is kind of allowed that you can have as many columns as you can in a table, but having big sized or too many columns in a table is kind of disadvantageous when you're doing quite a few bulk operations. So this is what we learned while doing our migration. Now the next phase that we are going to get into is more of query related patterns. This is all data model and insertion kind of more related to those. We'll go ahead with Shivang telling us about the patterns and the anti-patterns that we discovered while querying our SQL database for the first time.
Sorry. Hi everyone. So now I will talk about how we went about deciding the right indexes for our use case and what all things that we learned along the way. So we went ahead with we started analyzing our access patterns for read and writes, and we realized that we use tenant ID field for deleting tenants from our database. So we have we have one table in our database where we fetch the details about tenants from using a tenant ID. So we also needed these ID for deleting tenants from our database. We went ahead and created an secondary index on tenant ID. So yeah, like this seemed too easy for us at that time. So So then later on, we realized that uh, the index on tenant ID was a really bad choice for us, because the index on tenant ID created some hotspots and some fat indexes as the data grew. So suppose if one of the tenant have like if one of the tenant ID which is having a lot of data gets concentrated towards a certain shard. So we started seeing one of the shards having much more traffic or much more activity than the other shards. So as the data was between the tenants were uneven, so we started seeing query timeouts and cluster going down in some of the cases. So so we thought and thought, and one of the way we came up with was to distribute data evenly across shards. So how we do it? So we kind of stumbled across a function that Yugabyte provides. So this function is called YB hashcode. So what it does is it basically hashes. It uses the same hash function which Yugabyte uses internally to shard its data. So what we are doing here is, instead of creating an index on tenant ID, we are creating a index on we are creating a compound index where we say uh, create an index on tenant ID along with a mod value. So so we are saying that so basically we are creating a random ID which gets divided into n number of shards. So this random ID consists of the tenant ID and a mod value. So in this case, you are using 100 as a mod value. So this value can be anything uh, which suits the particular use case for your application. So for our application, we have used it as 100. Uh, so so now how we query uh, now our query patterns also changed back. So now instead of querying just tenant ID, we say delete. Instead of saying delete from table where tenant ID is something, we say delete from table where tenant ID is this, and we also mention the mod value, which are in this case would be from 0 to 99, and we delete this from each and every shard by using this. Uh, So the next step would be, the next key learning that we learned was that even fat charts can even be created using a secondary index also. I mean, we were initially we were aware that we should be aware of certain query patterns that can create uh, hotspots for us, but we were only thinking in terms of tables. We were not really aware that even secondary indexes can create fat charts. So yeah, that was one of the key learnings. And the second thing, we realized that we should use index only scans for performance critical queries, like for the queries that are we require to have really low latency. So by doing so, we have, by creating uh, index only scans, we have all the information of the index, and we don't have to go to multiple tables which are scattered into the multiple nodes. So I mean, this kind of scans become critical in distributed SQL system, where we have to reach out to multiple nodes for its data. Next. So now I will talk about some of the anti-patterns that we faced during our migration to YugabaDB. So, so yeah, so one of the key things would be to be aware of the bad query patterns that can affect your cluster. So you should always think in terms of distributed SQL database. Like in our case, we are using distributed SQL database. So your query design should also reflect that. So you should think in terms of cross server calls and what all things that the query you are designing can affect. So in our use case, there was one of the queries with in clause, which was having IDs known ahead of time. So for example, here we see the select star query, which has IDs up to and greater than 10,000. Like we were shifting from Mongo and we were converting the queries to SQL. So in Mongo, we didn't really care about the number of IDs because we were fetching in bulk, and Mongo, it's not a in Mongo it's okay to use uh, these number of IDs, as we were using a unsharded database at that time. So the second point is would be to second anti pattern would be to use aggregated queries. So like a count star query on a large table can prove to be an anti pattern. And next. So yeah, now I would like to talk more about these kind of queries. So like these kind of involves multiple tablets. So basically the YQL clients waits for all the tablets to respond and sends back an aggregated response. So these kind of queries can result in increase in latency and a reduced throughput. And we can quite a lot of times see query timeouts and cluster going down in some cases. So in the right, you can see one of our crashes that we faced due to this query, these query patterns. So, so alternatively, what we can do is we can use distributed parallel queries instead of querying 100 IDs using one query. We can divide the query into a number of queries, and we can query by hash partitions. So what we are doing here is, instead of querying all the IDs at once, we our query is confined to a single shard or a single tablet in case of gigabyte. Uh, like for example, here we see if we have uh, assuming we have 2 raised to power 16 hash keys, which is divided into 16 tablets, we can say we can divide a single query into 16 parts, and we can say select from table, where we provide a range of the tablet. Like in this case, the range would be from 0 to 2 raised to power 16 divided by 16. That would be 4096. And we can concurrently fetch all of the data from this tablet, send back and response. Yeah. Next. So yeah, so conclude, I would like to say that converting converting from NoSQL to SQL is a challenging task. But the most important thing is to analyze and research your patterns, your query patterns and data structure thoroughly beforehand, because you need a very strong foundation in SQL data model. So you should have a balance of the ideal solution which have in place, and also the time and effort that is required for it. Thank you. Yeah, we are also hiring. So yeah, please do reach out to us. Do you have any questions?